So we're going to begin chapter 20, which talks about electrochemistry. And in electrochemistry, all this does is it talks about the relationship between electricity and chemical reactions. And so these could be both spontaneous and non-spontaneous reactions that are involved in electrochemistry. Now, one thing that you've already learned about in your first lab this semester, you learned about oxidation reduction. And that's actually a kind of reaction that you learned about in Chem 1. And what's the key thing that you have to remember with redox reactions? What happens in redox reactions?
Something loses an electron and something gains an electron.
Okay, so there's going to be a transfer of electrons in a redox reaction. So we have to understand somehow a way to identify what's gaining and what's losing electrons. And we have names for those processes. We have oxidation. And what does oxidation involve? That's the loss of electrons. And so the opposite is reduction. And what does reduction involve? That's going to be the gain of electrons. And so what Bailey said is that something gains electrons and something loses electrons. That's actually a very good way to put it because oxidation and reduction always take place together. So if you have something that's being oxidized, you have to have something that's being reduced as well. Now, since we have two kind of opposite terms, oxidation and reduction, you need a way to remember the difference between oxidation and reduction. I hate Leo says Gur. I've hated it since 10th grade chemistry. What I like, especially since we're living in Oklahoma, oil rig. Oxidation is loss of electrons. Reduction is gain of electrons. So even today, I've been a chemist for, way too long. I still write out oil rig when I'm trying to remember the difference between oxidation and reduction, just to remember oxidation is loss of electrons, reduction is gain. So you want to remember that. Okay. So, how do we determine whether something is oxidized or reduced? The way we do that is we have to think about the oxidation numbers. And this is something that you already got some practice with at the beginning of the semester in lab. But there are some guidelines we can think about for oxidation numbers. So, an oxidation number is essentially the charge an atom would have if it were an ion. Of course, we know that a lot of atoms, for example, nonmetals and covalent compounds, they're not ions. But the oxidation number says, if it were an ion, what would its charge be? And so, generally, when we have covalent compounds, the more electronegative atom is going to act like the anion. And you'd kind of expect that because something like fluorine that's very electronegative, it's going to be pulling electrons more toward it. So if you have a covalent compound with two nonmetals, say oxygen and fluorine, fluorine as the more electronegative atom is going to have an oxidation number that's going to be more like an anion. It's going to have a negative oxidation number. So some guiding principles for assigning oxidation numbers. The sum of the oxidation numbers is going to equal the total charge on the molecule or ion. So if you're looking at identifying the oxidation numbers in phosphate, phosphate has an overall charge of -3. So your oxidation numbers for all the atoms better add up to -3. Okay, if you have a neutral molecule like carbon dioxide, your oxidation numbers better add up to 0 because carbon dioxide is neutral. So another one is you often start with what you know. Hydrogen is usually +1. There will be exceptions to that. For example, if hydrogen is combined with a metal, then hydrogen can have an oxidation number of -1. So really the only time you assign hydrogen a negative oxidation number is if it is combined with a metal. And we'll see an example of that here pretty shortly. Atoms that are in neutral elements also have an oxidation of number of 0. So something like hydrogen in diatomic hydrogen, H2, the hydrogens would have an oxidation number of 0. So that's kind of the rough guidelines. You usually want to start with what you know, like a hydrogen. Oxidation numbers often represent also what the charge would be if it were an anion. So example, oxygen. What would the oxidation number of oxygen usually be in a compound? -2, because oxygen ions are typically -2. So what about the halogens? What is the charge on the halide ions usually? Like fluorine, chlorine, bromine. It's -1, and so their oxidation numbers are generally -1. So you could start with hydrogen, the halogens, or the oxygen. If you know those, then you can figure out what the other oxidation numbers are going to be. Okay, so explain B.
It's a covalent, I believe, and I think chlorine's got the higher electronegativity, so it's going to be the anion. So it would be a -3, and then fluorine would be a +1, and there's 3 of them.
Okay, is chlorine going to be the anion?
Or does electronegativity increase from bottom to top?
Yes.
So then reverse that.
Okay, so the fluorine's the anion.
Do the opposite of what I said.
So that means that what we know here is that the fluorine is going to be -1. And there's 3 of them. So there's a total of -3 charges from the fluorines. So what does the chlorine have to be to balance that -3? That one chlorine has to be a +3. Okay? So, red group, since you volunteered, which one do you want to do next?
Let's do C.
C, okay. Tell me about C.
Well, it's a hydrogen with a metal, and so the hydrogen would be -1.
Okay, so the hydrogen is acting like an anion, so that's going to be -1. Another way you might look at that is, even though you might not explicitly have been told this, usually the more electronegative atom is further to the right in the formula. And so that's hydrogen in this case. And so the hydrogen is going to act like the anion. That's another way you might look at that. And so if hydrogen as an anion is -1, then the potassium must have an oxidation number of +1 to balance that. So easy enough. Okay, so let's do the green group. You're stuck with phosphoric acid.
Well, it's for hydrogen we have +1, that's regular. For oxygen -2, and phosphorus is with +5.
Because, for example, if each of the oxygens is -2, so you have 8 negative charges, and then 3 positive charges from the hydrogen, so that leaves you 5 positive charges for the phosphorus. So again, you start out with what you know, and then you can deduce what you don't know. And so I know purple group over here was a little shocked that chlorine might have something like a +3 oxidation number. That's fine. Sometimes some of these halogens end up with very positive, like +5, +7 oxidation numbers. So again, that's not saying they really are that charge. That's saying if it was an ion in that molecule, that's what it would be. Okay, so any other questions about oxidation numbers? Everyone happy with those?